All right, let's get right into it. What if I told you that most coding interview problems, they really just boil down to three core ways of thinking? Mastering these mindsets is the secret. But look, it's not just about knowing what they are. The real magic is knowing exactly which one to pull out of your back pocket and when.
So to really get our heads around this, let's imagine we're planning a road trip. The greedy approach? That's simple. You just take whatever road looks fastest right now. No questions asked. Dynamic programming, on the other hand, is like being a meticulous planner. You'd pre-calculate the best routes between all the major cities and then build your perfect trip using that saved info. And backtracking? Well, that's the explorer. You try one route, and if it turns out to be a dead end, you don't panic, you just turn back and try another path. Three totally different ways to tackle the same journey. So first up, let's meet our first hero, the optimist. This is the greedy algorithm, and its whole personality is built around being fast, keeping things simple, and always making the choice that looks best in the moment, hoping that it all works out perfectly in the end. So officially, a greedy algorithm makes what's called a locally optimal choice at every single step. It's basically got blinders on. It picks the most appealing option right in front of it, and it never, ever looks back or reconsiders. The big gamble here is that if you keep making the best short-term decision, you'll magically end up with the best overall or global solution. And here's a classic example where our optimist is absolutely right. It's called interval scheduling. Imagine you're trying to schedule as many meetings as possible in one day without any of them overlapping. Well, the greedy strategy is not only simple, it's provably correct. So here's how it works. First, you sort all the meetings by when they finish. Then, you just pick the very first meeting on that list. After that, you just walk down the list and grab the very next meeting that starts after your last one ended. That's it. Simple, elegant, and it just works. And this brings us to the biggest selling point for greedy algorithms. They are blazing fast. The time complexity is usually just O of n log n, which, if you think about it, is pretty much just the time it takes to do that initial sort. After that, it's just a single, quick pass through the data. When this approach works, it's unbelievably efficient. But this leads us to the million-dollar question, doesn't it? Is the choice that looks best right this second always going to lead to the best possible outcome in the long run? This is the potential Achilles heel of our optimist. And this slide just nails the problem perfectly. Take the classic 0 to 1 knapsack problem. You've got a backpack with a weight limit and a bunch of items with different weights and values. Now, a greedy approach might be to just keep picking the item with the highest value to weight ratio. Sounds smart, right? But what if you pick a small, really efficient item that uses up the last bit of space in your bag, and in doing so you miss out on taking two slightly less efficient items that when added together would have given you a way higher total value? That's where our short-sighted optimist fails. So, to solve problems like that, we need a different hero. Meet the planner, also known as dynamic programming. This approach is methodical, it's powerful, and it completely avoids the short-sightedness of the greedy strategy, because its whole deal is to remember what it's already figured out.
Okay, so here's the core idea. Dynamic programming, or DP, works by breaking a giant problem down into a bunch of smaller, easier-to-solve subproblems. It solves each little subproblem exactly once, and then it saves that answer, kind of like jotting it down in a notebook. Now, for DP to even be an option, the problem needs to have two key properties. First is optimal substructure, which is a fancy way of saying the best solution to the big problem is built from the best solutions to the small problems. And second is overlapping subproblems, which just means you'd be solving the same little problems over and over again if you didn't bother to save the answers.
And this is exactly how our planner conquers the knapsack problem. Just look at this table. It's methodically calculating the best possible value for every item at every single possible capacity. For each little box in this grid, it asks a simple question. Is it better for me to include this new item, or should I stick with the best solution I already found without it? It builds on previous answers. By the time it gets to that final cell in the bottom right, it has already explored every valid combination and guaranteed the absolute best answer. And there it is. You can see it right there. The optimal value is 220.
Now, DP usually shows up in two main flavors. On the left, you have memoization, which is the top-down approach. You start with the big problem and use recursion to break it down, storing or memoizing the results as you go. On the right is tabulation, which is what we just saw. It's bottom up. You start with the tiniest possible subproblems and build up, step by step, filling out a table until you reach the final answer.
Now, our planner is incredibly reliable, but that power comes with a price tag. the time complexity is usually polynomial. For Knapsack, it's based on the number of items times the capacity of the bag. That's definitely slower than Greedy. And it can be a real memory hog, because you need that big table to store all the subproblem answers.
But what about problems where you need to find all the possible solutions? Or, what if you're trying to solve something like a Sudoku puzzle with a complex set of rules? For that kind of challenge, we need our final hero, the explorer. This is backtracking. At its heart, backtracking is a really clever, systematic search. It tries to build a solution one piece at a time. And the very moment it places a piece that breaks a rule, it doesn't just keep going, it immediately gives up on that entire path. It backtracks and tries a different choice from the step before. So the key word here, its absolute superpower, is pruning. By intelligently chopping off entire branches of possibilities that it knows will lead to a dead end, it saves itself a massive amount of work. This is exactly what makes it a practical solution for those classic puzzles like placing end queens on a chessboard or solving any Sudoku you throw at it.
Okay, now the worst case time complexity can look, well, absolutely terrifying. N factorial is a ridiculously huge number. But here's the secret. The whole point of backtracking is that thanks to smart pruning, you almost never actually explore that entire massive space. The theory looks scary, but the practice is smart.
All right, so we've met our three heroes, the optimist, the planner, and the explorer. Now for the most important part. How do you build this into a real-world playbook you can use when you're staring down a new problem in an interview? This table really lays it all out side by side. You've got the optimist, whose whole philosophy is make the best local choice. Then there's the planner, who's all about solve and store subproblems. And finally, the explorer, who lives to explore and prune possibilities. You reach for Grady when you can prove a simple choice is always safe. You use DP when you see that perfect combo of optimal substructure and overlapping subproblems. And you call on backtracking for anything involving constraints or finding every single solution. So here it is, your actionable 3-step game plan. Step 1. Always try to find a greedy solution first. It's the fastest and simplest. Ask yourself, is there one simple local choice that I can prove is always the right move? If you can't prove it, move on. Step 2. Look for a DP pattern. Can you write a formula, a recurrence relation, that defines the big problem in terms of smaller versions of itself? If you can, but the number of states you'd have to save is just gigantic, then it's time for step 3. Switch to backtracking. This is your tool when you need to find all solutions or navigate a complex web of rules. Just explore and prune. So let's boil it all down to the essentials. 1. Greedy is fast, but it's fragile. You absolutely need to be able to prove that it works. 2. Dynamic programming is your powerhouse for optimization problems, but you have to find that clear recurrence and the memory usage needs to be manageable. And 3, backtracking is your go-to explorer for constraint and enumeration problems, and its real-world speed is all about how well you can prune away the dead ends. So there you have it. You now have the map. You have the optimist, the planner, and the explorer in your mental toolkit. The only question left is, what problems are you going to solve now?